So what is called a relation on a set X is just a subset of X cross X. That is, R is some set of ordered pairs, X1, X2, contained in X cross X. X cross X is the set of all ordered pairs. Okay, so if you take the direct product of two sets, it's the set of ordered pairs. If you take the direct product of a set with itself, it's again the set of ordered pairs where the first and second coordinates come from X. And a relation is just some collection of ordered pairs. So we say that if X1, this is just general nonsense in mathematics. If X1, X2 is in the relation R, then X1 and X2 are, you might say, they're related. And sometimes you write X1, this squiggle X2 means they're related in general. But the important example, or a special case of the important example, is suppose we let X be Z. This means the set of all integers, positive and negative and 0. So Z cross Z is just the set of all ordered pairs, X1 and X2, where X1 and X2 are integers, right? This is just all ordered pairs. If you looked at this in the plane, it would just be the points in the plane where all the coordinates were integers, right? So if this is the plane R2, Z2 is just the lattice points, okay? So this is all just sort of a setup, but there can be questions about this. This is really just language and notation. So a relation on Z is just a set of ordered pairs of integers. Right? I mean, that's just a relation on the integers of any sort. And in the example, I'm giving you a very special but very nice relation. I have to tell you, how do you decide what pairs of integers are in the relation? So I'm going to construct or define the relation, which is called congruence modulo 3. So we say that X1 and X2 are in the relation if X1 minus X2 is divisible by 3. Okay. So for example, 19 and 7 are in the relation because if you take 19 minus 7, that's 12, and that's divisible by 3. It's 3 times 4. So this is in the relation. 19 comma 8 is not in the relation because 19 minus 8 is 11. If you divide that by 3, you get a remainder of 2. So 3 doesn't divide 11. And the notation that we use for congruence is X1 congruent to X2 mod 3, or modulo 3, if 3 divides x1 minus x2. So this is a relation. Certain pairs of integers are congruent mod 3 and others are not. So 19 is congruent to 7 mod 3. That's the proof. 19 is not congruent to 8 mod 3. That's the proof. Okay.
Professor, quick question.
Yeah.
How come you do 3.3 plus 2?
It's not 3.3. It's 3 times 3. I'm
Oh,
dividing 3 into 11.
Okay, that makes more sense then. I thought you wrote 3.3.
No.
Okay.
Right. 3 times 3 plus 2 is 11.
Yes, yes.
3 times 4 is 12. And I will show that congruence modulo 3 is a very important kind of relation called an equivalence relation. So you have to know, this is very important, what is an equivalence relation? An equivalence relation is a relation that is reflexive, symmetric, and transitive. Has these 3 properties. What does reflexive mean? An equivalence relation, let's say, on a set X. X is related to itself for all X in the set capital X. That's what it means to be reflexive. What does symmetric mean? It means that if X and Y are in the set and X is related to Y, then Y is related to X. Right? So there's a symmetry, you can flip this around. And transitive means that if X, Y, and Z are in the set, and X is related to Y, and Y is related to Z, then X is related to Z. Right? So this is the definition of an equivalence relation. And I want to show X congruent to Y mod 3 is an equivalence relation. That is, I want to show that this relation between pairs of integers is reflexive, symmetric, and transitive. So how do we prove it's reflexive? Well, for all integers x, x minus x is 0. And 0 is divisible by 3. 0 is 3 times 0. So x is congruent to x mod 3. Every integer is congruent to itself. So therefore, this relation is reflexive. If x and y are integers, and x is congruent to y mod 3, that means that x minus y is divisible by 3. It's 3 times q for some integer q. For some q and z. But if x minus y is 3q, if if I multiply by -1, y minus x is minus 3q, right? Which is 3 times minus q. But q is an integer, minus q is an integer. They don't have to be positive, they just have to be integers. So 3 divides y minus x. So y is congruent to x mod 3. So this is the symmetric property. If x is congruent to y mod 3, then y is congruent to x mod 3. And what about the transitive property? So if x, y, and z are integers, and x is congruent to y mod 3, and y is congruent to z mod 3, then what does that mean? It means that x minus y is a multiple of 3 times q. And y minus z is another multiple of 3. Let's say 3 times q prime. And what happens if I add these equations? The y's cancel. I get x minus z is 3q plus 3q prime. Factor out the 3, that's 3 times q plus q prime. So x minus z is again a multiple of 3. So x is congruent to z mod 3. So it's worth spending a minute just to look at this proof, because it's very important. It shows you the definition of an equivalence relation verified in a very concrete, that is not abstract in any way, example. Okay. Any questions about this?
No, that was good. I like that.
Okay. And then we have the definition of an equivalence class. If R, or let's just say let
Can you move the paper down? Yeah, thank you.
R be an equivalence relation, on a set X, what is called the equivalence class of X is the set. I'll write it as X subscript R, square brackets around the X, or just X. This is the set of all Y and X that are related to X. X is related to Y. That's the equivalence class. So for example, if R is the relation of congruence modulo 3 on the integers, then the equivalence class of any integer X is the set of all Y such that X is congruent to Y mod 3. Everything related to X. So this is the set of all integers Y such that X minus Y is divisible by 3 is 3Q for some integer Q. Or you can write this as the set of all y, such that y equals x minus 3q for any integer q. Or if you, since q can be positive or negative, I can also write this as all y, so that y equals x plus 3q for any integer q. So for example, what is the congruence class of 0? Mod 3 is a set of all integers y. If x is 0, y equals 3q. All multiples of 3. That's 0, 3, 6, 9, 12, or minus 3, plus or minus 3, plus or minus 6, and so forth. All right. The set of all multiples of 3, that's the equivalence class of 0. The equivalence class of 1 is all integers, such that y is congruent to 1 mod 3, which is all integers y, such that y can be written in the form 1 plus 3q. This is all integers that leave a remainder of 1 when you divide by 3. So you have 1, 4, 7, 10, and so forth, minus 2, minus 5, minus 8. You have this infinite set of positive and negative integers. These are all the integers that leave a remainder of 1 when you divide by 3. And the equivalence class of 2 is all integers which are congruent to 2 mod 3. This is all integers of the form 2 plus 3q. So you get 2, 5, 8, 11, minus 1, minus 4, minus 7, and so on. You have these 3 infinite sets of integers. And those are the equivalence classes. But for congruence, they're called congruence classes. Mod 3.
Professor,
Mm-hmm.
does it matter that in the congruence class, that in the set, that some of them aren't divisible by 3?
I don't understand what you're asking. So the congruence class of 0 contains all the numbers that are divisible by 3.
Yes.
The congruence class of 1 cannot contain any element which is divisible by 3. It only contains elements which leave a remainder of 1 when you divide by 3. Right? So you know from when you first learned division, if you divide 3 into some number n, you get some quotient q and a remainder r, right? You can write every number. If you divide a number by 3, it's 3 times q plus r. Q is the quotient, r is the remainder, and the remainder is 0, 1, or 2, right? So if you have 17,
we have 3 separate classes.
Sorry?
So we would have 3 separate classes with either
Yes.
1 remainder, 1 remainder, or 2 remainder.
Correct. So 17, if you divide it by 3, leaves a remainder of 2. Minus 17, if you divide it by 3, what's the remainder going to be?
It'll still be 2.
Why is it 2?
Because it's a negative 17, or would it? Yeah. So it'd be 3 times negative 5. Oh, minus 2.
Right. So what's the remainder when you divide minus 17 by 3?
It'd be -2.
But -2 is not allowed. A remainder is 0, 1, or 2, nothing else.
Yeah.
Can't have a remainder of -2.
So would you do 3 times 6 plus 1? 3 times -6 plus 1?
So 3 times -6 is -18, plus 1 is -17. So the remainder is 1. 3 times, sorry, -6. Yeah. 3 times -6 plus 1 is -17. So the quotient is -6, and the remainder is 1. Suppose I divide 89 by 5. What's the quotient and the remainder? And divide -89 by 5. And tell me what is the quotient and what is the remainder? Right.
Five times 17 plus 4. So.
Okay. 5 times 17 is 85 plus 4 is 89, right? 89 equals 5 times 17 plus 4. Good. So the quotient is 17 and the remainder is 4. What about -89? When you divide it by 5, what do you get?
And should do 18 remainder 1.
So -89 is
One
5 times -18. That's -90 plus 1. So the quotient is -18 and the remainder is +1. Right? So have to. So it's just doing arithmetic carefully, right? Got to be careful. Any questions about this? Let's go back to looking at equivalence relations and equivalence classes. So suppose R is an equivalence relation on a set X, and square brackets little x is the equivalence class of an element X in the set X. So if here's the set X, sitting in that is a subset, which is the equivalence class of X. This is the set of all Y and X, such that X is related to Y. And because R is reflexive, that means X is always related to itself. So X is always a member of the equivalence class of X. Right? So every element of the set X belongs to at least one equivalence class. Suppose we take two elements, Y and Z, in the set X, or suppose we take two elements, yeah, doesn't matter what I call them, Y and Z in the set X. And suppose if I take the equivalence class of Y and the equivalence class of Z, there's some element little x, which is in the intersection. So you have two equivalence classes and X is in both of them. I claim then that the equivalence class of Y has to equal the equivalence class of Z. That is, if I had two equivalence classes and they had some element in common, they're actually equal. So if X is in the equivalence class of Y, that means, sorry.
Can you lower the paper, please, Professor?
Sorry?
No, I was just asking to lower the paper.
Yeah, okay. So I claim these two are equal. So I must show the equivalence class of Y is contained in the equivalence class of Z, and the equivalence class of Z is contained in the equivalence class of Y. That's what it means for two sets to be equal. Each is a subset of the other. So let me prove this. Let W be in the equivalence class of Y. That means Y is related to W. But also X is in the equivalence class of Y, right? Which means Y is related to X. But by the symmetric property, this means X is related to Y. This is bireflexive. And if X is related to Y and Y is related to W, then by the transitive property, X is related to W. But also, since X is in the equivalence class of Z, this means X is related to Z. That's the definition. Sorry, Z is related to X. And if X is related to W and Z is related to X, again, by the transitive property, Z is related to W, which means W is in the equivalence class of Z. So what I proved is that for every element W in the equivalence class of Y, that element W is also in the equivalence class of Z. So that means that every element of this class is in this class. That proves this inclusion. And you can run through the same argument interchanging Z and Y, and I would prove this. So these two guys are equal. So what this says about equivalence classes is for all Y and Z in the set X, either the equivalence class of Y equals the equivalence class of Z, or the equivalence class of Y and the equivalence class of Z are disjoint. That means their intersection is the empty set. So when I look at the set X, the set X is partitioned into equivalence classes. the different equivalence classes with respect to the relation. So if we take the relation congruence modulo 3, this is defined on the set of integers, and there are 3 congruence classes. The congruence class of 0, which is all the multiples of 3, the congruence class of 1, which is all numbers that leave a remainder of 1 when you divide them by 3, and the congruence class of 2. Which is all numbers that leave a remainder of 2 when you divide them by z. Okay. And just because this is so important, I want to keep on talking about congruence. Suppose we let m be a positive integer. Let's say m is at least 2, and define the relation congruence modulo m. So we say that x is congruent to y mod m. This is a relation on the integers. If m divides x minus y. So the example I gave above was in the case m equal 3, but this is true for any m. For example, we already saw in the case m equal 2, the congruence class of 0 mod 2 is the set of all even integers. And the congruence class of 1 mod 2 is the set of odd integers. And if you take the integers, z is partitioned into 2 congruence classes, even and odd. 0, 2, 4, and so forth. 1, 3, 5, and so forth. Minus 2, minus 4, minus 1, minus 3. Right? So if you take m equal 2, there are 2 congruence classes, even numbers and odd numbers. If you take m equal 3, we saw 3 congruence classes, depending on the remainder when you divide the integer x by 3. So let's just remember what is called the division algorithm. I'm going to actually prove this next week, but this is just long division. So that n and m be integers where m is positive, then you can write n. When you divide it by m, you get a quotient q plus a remainder. This is called the quotient. This is called the remainder, where r is a non-negative integer between 0 and m minus 1. And q and r are unique. If you divide one number by another, there's always a unique quotient and a unique remainder, where the remainder is always between 0 and m minus 1. So for example, if n is, I don't know, 3,927 and m is 72, let's see, what happens if you divide n by m? You want to find q and r, find the quotient and the remainder. So you just divide 72 into 3,927. I think this goes 5 times. Let's see, I think this is right. So this goes into this 4 times. You subtract, you get 39. So 3,927 is 72 times 54 plus 39. And that's the quotient. And that's the remainder. Right? And moreover, when you do this division, n minus r is m times q. So if you take a number, divide it by m, and r is the remainder, n minus r is a multiple of m. So n is congruent to r mod q. Sorry, mod m. Right? So if you look at congruence modulo m, every integer is congruent to its remainder, which means n is in the congruence class of R. Okay. So for every integer m at least 2, if you take n in Z, write n is mq plus r. N is congruent to r mod m. Or another way of saying that is n is in the congruence class of R. So you have R in this set, there are m integers in this set. So every integer is in one of these m congruence classes. And I claim that if R1 and R2 are in this set, say R1 is less than R2, less than or equal to m minus 1, then the equivalence class of R1 and the equivalence class of R2 are different. So each of these m congruence classes is distinct. And what is the proof of this? If n is in both of these congruence classes, then you can write n as mq1 plus r1. This just means n has a remainder of r1 when you divide by m, and n is also equal to mq2 plus r2. Right. If n is in the congruence class of R1, you can write n like this. If n is in the congruence class of R2, when you divide n by m, you get a remainder of R2. So you get mq1 plus R1 equals mq2 plus R2. I can rearrange that as mq1 minus mq2 equals R2 minus R1. And here I can factor out an m. This is m times q1 minus q2 equals R2 minus R1. But R1 and R2 they're between 0 and m minus 1. So this difference is certainly less than m. And it's positive. But that's not possible because this says if I divide by m, this is an integer between 0 and 1. And there's no integer between 0 and 1. Strictly between 0 and 1. That's impossible. So therefore, if R1 is different from R2, and they're both in this set from 0 to m minus 1, the equivalence classes have no element in common. They're disjoint. So if you take the integer z, you have all these m congruence classes. And they partition z. And what we write as z sub m, or sometimes z mod mz, this is the set of congruence classes. So for example, Z2 consists of the congruence classes 0 and 1. So this is a set with two elements, and one element is the set of all evens, and the other is the set of all odd numbers, odds. Right? So Z2 is a set with two elements, but each element is an infinite set of integers. Any questions about this?
Just to reiterate, the last thing you said was that Z mod 2 gives you the set of these two equivalence classes, which
Correct.
have sets of infinite evens and infinite odds.
Well, so each equivalence class is an infinite set of integers.
Yes.
So the equivalence of 0 is the set of all even numbers, and the equivalence class of 1 is the set of all odd numbers.
Yes.
Now, there's a nice way to do arithmetic with congruences. So again, let's fix the number m, which we call the modulus. M could also be equal to 1, but it's easier just to make it always greater than or equal to 2. And we write A is congruent to B mod M if M divides A minus B.
If it divides what?
A minus B. That's the definition of congruence.
Okay.
Or maybe just so I fix the notation so it's similar to what is in the book. Doesn't make any difference, of course. We can say that A is congruent to A prime mod M if M divides A minus A prime. So let's suppose we have integers A prime, B, and B prime. A is congruent to A prime mod M, and B is congruent to B prime mod M. And I'm going to prove we can add and multiply congruences. So what does this mean? If A is congruent to A prime mod M, this means A is A prime plus some multiple of M, right? A minus A prime is divisible by M. And if B is congruent to B prime mod M, that means B is equal to B prime plus M times something, I don't know, call it K. It doesn't matter what letters we use. In fact, maybe I'll just call, well, that's fine. So A is A prime plus M cubed, B is B prime plus MK. So A plus B is A prime plus MQ plus B prime plus MK. If I rearrange that, that's A prime plus B prime plus MQ plus MK. That's A prime plus B prime plus M times Q plus K. Q plus K is just an integer. So this number is this plus a multiple of M. So A plus B is congruent to A prime plus B prime mod M. So this is a proof that we can add congruences mod M. The modulus has to be the same. So if A is congruent to A prime mod M and B is congruent to B prime mod N, then you can add.
Professor, can you just slide a little bit to the right?
Yeah, this just says we can add. So for example, eight is congruent to 2 mod 3. Minus 19 is congruent to 5 mod 3. Why is that? 8 minus 2 is 6, which is 3 times 2. Minus 19 minus 5 is minus 24, which is 3 times minus 8. And you can add, so you get minus 11 is congruent to 7 mod 3. And if you want to check, minus 11 minus 7 is minus 18, which is 3 times minus 6. So this is just an example of adding congruences. Right?
Professor, can you just go back to the last page for 1 second? Thank you. I'm good, thank you.
By the way, you learn about congruences when you learn to tell time, because suppose you let m equal 12. So remember, you have a clock. So let's say it's 8 o'clock. And 9 hours later, what time is it? 8 plus 9, that's 17. But you don't say it's 17 o'clock. You say 17 is congruent to 5 mod 12. So if it's 8 o'clock and you add 9 hours, you get to 5 o'clock, right? So telling time, reading a clock, is just learning how to do arithmetic modulo 12. If you're on military time and you say it's 1700 hours, what is it 9 hours later? You don't say it's 26, you say it's 2 o'clock. Right? Right? 1700 hours, 9 hours later, it's 2.
Would that be mod 24?
Mod 24, yes, sir. So I showed a moment ago that you can add congruences, but you can also multiply them. So suppose A is congruent to A prime mod M, and B is congruent to B prime mod M. I claim that A times B is congruent to A prime B prime mod M. Right? I claim you can multiply congruences modulo M. So how do we prove the claim? If A is congruent to A prime mod M, That means A is A prime plus M times Q for some integer Q. And if B is congruent to B prime mod M, then B is B prime plus MK for some integer K. And what about AB? Well, A times B, A I can write as A prime plus MQ, and B I can write as B prime plus MK. Let me just multiply this out. This is A prime B prime plus A prime MQ plus MQ B prime plus MQ MK, which is A prime B prime plus all of this. And I can factor an M out of each term. I get A prime Q plus QB prime plus QMK. But this is just an integer. This is A prime B prime plus ML for some integer L, which is equal to this. Which means AB minus A prime B prime is a multiple of M. So AB is congruent to A prime B prime mod M. Let's look at an example. A moment ago, I had A congruent to 2 mod 3 minus 19 congruent to 5 mod 3. So what is 8 times minus 19? That's minus 152. And what's 2 times 5? That's 10. And minus 152 minus 10 is minus 162. That's divisible by 3. That's 3 times minus 54. So I have 8 is congruent to 2, minus 19 is congruent to 5, and 8 times minus 19 is congruent to 2 times 5 mod 3. This is just a numerical example of the fact that we can multiply congruences. Okay, let's just do another sort of practice problem. We have 11 is congruent to minus 3 mod 7, and 19 is congruent to 5 mod 7. So check the following. 11 plus 19 is congruent to minus 3 plus 5 mod 7. And 11 times 19 is congruent to minus 3 times 5 mod 7. So just do the arithmetic to check that these work. Let's see. What is 11 plus 19?
30.
What is minus 3 plus 5?
2.
And is 30 congruent to 2 mod 7?
Yes,
Because?
because it's 7 times 4 is the 28.
All right, so 30 minus 2 is 28 is 7 times 4. Let's see, this one's harder. What's 11 times 19?
209.
That's 209. And minus 3 times 5 is minus 15. See, if we subtract 209 minus 15, that's 209 plus 15. That's 224. Is that divisible by 7?
Yes, by 32.
So divide 7 into that, you get 32. So everything works the way it's supposed to. Right. Any questions about this? Now, the fact that we can add and multiply congruences gives us a way to add and multiply congruence classes. So let's fix a modulus M at least 2 and let A and B be integers. So I want to define, if I can, how do we add a congruence class of A plus the congruence class of B? So let's see. I want to find a C such that this congruence class plus this congruence class is this congruence class. So we can say the following: if A prime is any integer in the congruence class of A, then A is congruent to A prime mod M. And if B prime is any integer in the congruence class of B, then B is congruent to B prime mod M. But I just proved I can add congruence classes. So A plus B is congruent to A prime plus B prime mod M, which means A prime plus B prime is in the congruence class A plus B. So for any representative A prime of the congruence class A and any representative B prime of the congruence class of B, A prime plus B prime is in the congruence class of A plus B. So I define the sum of the congruence classes of A and B to be the congruence class of A plus B. And this makes sense because this is completely well defined. No matter what element of this class I pick, and no matter what element of this class I pick, I get an element of this class. So this is an addition So this defines addition on the set of congruence classes mod M. I can add congruence classes. So this is really very interesting. But let's just look at the very simplest case of this, which they taught you in elementary school. What I mean by that is, in elementary school, they taught you that if you take an even number plus an even number, you get an even number, right? An even number plus an odd number is an odd number. An odd number plus an even number is an odd number. And the sum of two odd numbers is even, right? So everybody happy with that?
Yeah.
Is that okay?
Yes.
So if we look at Z2, or Z mod 2Z, this consists of two congruence classes, the even numbers and the odd numbers. And what's our addition table say? If we take 0 plus 0, that's 0 plus 0, which is 0. This says an even number plus an even number is an even number. 0 plus 1, that's the congruence class of 0 plus 1, which is 1. An even number plus an odd number is an odd number. And 1 plus 1, that's the congruence class of 1 plus 1, which is the congruence class of 2. But 2 is congruent to 0 mod 2, so that's the same as the congruence class of 0. So this says an odd number plus an odd number is an even number. Right? So we have a nice way to do addition of congruence classes. And this addition of congruence classes satisfies very nice properties. So for example, suppose we're looking at addition of congruence classes. In Z mod MZ. So if I take the congruence class of A and the congruence class of B, and I add to that the congruence class of C, what do I get? Well, this is the congruence class of A plus B, plus the congruence class of C. And this is, by addition formulas for sum of congruence classes, the congruence class of A plus B plus C. But inside the square bracket, we just have integers. And we know addition of integers is associative. This is the same as A plus the congruence class, A plus B plus C, because this number equals this number. And this is the congruence class of A plus the congruence class of B plus C. And this is the congruence class of A plus congruence class of B plus congruent class of C. So this says addition of congruence classes is associative. Of course, we also know that if we take the congruence class of A plus the congruence class of B, that's the congruence class of A plus B. But for integers, A plus B equals B plus A. So this is the congruence class of A plus the congruence class of B plus the congruence class of A. So this says addition of congruence classes is commutative. We can interchange the order of addition. And if I take the congruence class of A plus the congruence class of 0, that's the congruence class of A plus 0, and A plus 0 is just A. So this congruence class of 0, which is the set of all multiples of M, is like the 0 for addition in this set of congruence classes. And finally, for any A, if I take the congruence class of minus A and add them, that's the congruence class of A plus minus A. That's A minus A, that's 0. So we have the inverse under addition. If I take the congruence class of A, its inverse under addition is the congruence class of minus A. And we can now define subtraction. The congruence class of A minus the congruence class of B is the congruence class of A minus B. So we can do arithmetic, additive arithmetic for congruence classes. And in exactly the same way, we can multiply congruence classes. So mod M. So the congruence class of A times the congruence class of B, we can define that unambiguously as the congruence class of A times B. And then you can check all the nice properties of multiplication also hold. If you take A congruence class of A times the congruence class of B and multiply that by the congruence class of C, this is the congruence class of AB times the congruence class of C. This is the congruence class of AB times C. But for integers, AB times C is the same as A times BC. So that's the congruence class of A times the congruence class of BC, which is the congruence class of A times congruence class of B times the congruence class of C. So this is the distributive law for multiplication. And so it's really very interesting. We can carry over addition and multiplication from integers to congruence classes mod M. And we will see that this is an extremely important construction in algebra. We will come back to this very, very often. And yeah. Any questions about this? Is this okay? If you just want to see, for example, an example, oh, here's something interesting. Suppose I take M equal to, let's say, 7, and I take the congruence class of 2, times the sum of the congruence classes of 3 and 4. So that's the congruence class of 2. Maybe I'll make this 5 so it's not so trivial. Times the congruence class of 8. Because 3 plus 5 is 8. Of course, 8 is the same as 1, mod 7. So that's the congruence class of 2 times 1. So this is the congruence class of 2 times 1, or the congruence class of 2. What's the congruence class of 2 times the congruence class of 3 plus the congruence class of 2 times the congruence class of 5? I just want to check the distributive law works. So I distributed this across. If this were true, I should get the same thing. So this is the congruence class of 6, and this is the congruence class of 10. That's the congruence class of 16. But mod 7, 16 is the same as 2. So these are exactly the same. So this is an example of the distributive law. 2 times 3 plus 7 equals 2 times 3 plus 2 times 7. So everything I've done is on pages 10, actually basically all on page 10 of the book, but I've spent an hour or so going through it in detail because it really is quite important. And any questions about this? Okay. I still have to post a homework assignment for next week, and I will do that probably this evening. Okay. All right. If there are no more questions, then we are done for the morning.
Thank you, Professor.
Bye all.
Thank you, Professor.
Thank you, Professor.
Thank you.